Hello, good morning. Good morning, everybody. Today we have the great honor to have Dr. Tatiana Novikova as our speaker. Dr. Novikova is a very good friend and a collaborator all the way from Paris, France. She's the head of the Characterization and Modeling Division of the Laboratory of Physics of Interfaces and Thin Films at Ecole Polytechnique. And I'm sure she will have few slides to explain to us what Ecole Polytechnique is, but it's #1 engineering school in France, FYI. She received a master's degree in applied mathematics from the Moscow State University in Russia, and a PhD in applied physics and mathematics from the Moscow Institute of Mathematical Modeling and the Russian Academy of Science, and HDR, which is a habilitation in physics from the Palaiseau University in Orsay. Her research activities are focused on optical polarization and interaction of polarized light with matter, and fundamental aspect of Mueller polarimetry and its application for semiconductor metrology and biomedical diagnostic. She's the recipient of many awards, and overall the most prestigious award in this context, in polarization specifically, which is the G.G. Stokes Award, that is awarded by SPIE, and she is the recipient of this award in 2020, so fresh new awardee. She was also guest editor of a special issue on biomedical optics and polarization in the Journal of Biomedical Optics, and she has published extensively. And one day she will have a NIH grant with me at some point. Yeah. Thank you, Tatiana, for coming all the way from France to our department. And I leave it to you.
So good morning in Florida. It's already afternoon in Paris. I'm very happy that everybody wakes up to attend my lecture. And I will talk today about the optical polarization actually as a thread which helps us with the biomedical diagnostics. I'm sure you know this Greek myth about Ariadne, who found her way from the labyrinth. And I hope that optical polarization will help us to do the same. And as Jessica correctly noted, I will say a few words about my institute, the Ecole Polytechnique. It's an engineering school in France, and it's located, you see the red spot, just 20 kilometers south of Paris nowadays. And it's a school of military engineers. And a little bit about the history. The school was founded in 1794. It means that last year we celebrated its anniversary, 225th anniversary. And you see the picture of the old building. It's in the very center of Paris, Rue Mouffetard. In 1805, Napoleon gave Ecole its military status, its uniform, and its flag. And it was a purely boys' school till 1972, when girls got right to pass exams and to enter Ecole Polytechnique. And contrary to other French universities, to become a student at Ecole Polytechnique, you need to pass exams. And then school moved in 1976 to Plateau-Saclay, to the outskirts of Paris. Our campus, it's a fast line of metro, 30 minutes you are in the center of Paris. Last year, 2019, Ecole Polytechnique becomes part of the Institut Polytechnique de Paris. It's a big umbrella structure which includes many engineering schools. And in this year, 2020, it was ranked as a second world's best small university after Caltech. And to sum up, we can say that Ecole Polytechnique is the most prestigious graduate institute of science and technology in France. And it's not only students, we have a big research center, we have 21 laboratory, physics, chemistry, biology, everything. And this is a few words about my laboratory where I am work now, Laboratory of Physics of Interfaces and Thin Films. We are about 120 people from more than 30 countries, and we have 4 big groups. First group, historically, it was like the one from which laboratory starts. It's the group working with the silicon materials and applications, photovoltaics in particular. Another group, second group, it's a group working with nanocarbon and electronic devices. Third group, it's organic and large area electronics. And my group where I'm working, it's applied optics and polarimetry. And this year we have some structural reorganization. So now I am the head of the characterization and modeling pool, but still I'm doing optics and polarization. And this is the outline of my talk. First, I will recall briefly the fundamentals of light polarization, describe shortly 2 formalisms which we can use for the description of polarized or partially polarized light, namely Jones and Stokes-Mueller formalism, and give you a few examples of polarimetric techniques. Then I will present the instruments which we are using here and the data processing algorithms. And then we'll focus on the biomedical application of Mueller polarimetry. It is known that a fully polarized monochromatic wave propagating in a homogeneous medium is a solution of to the Maxwell equations, and it can be presented in a complex form like the top equation. And if we choose an appropriate coordinate system where z axis is aligned with the direction of wave propagation, the electric field of this propagating electromagnetic field can be described by 2 components only. You see that z component is equal to 0 in this system of coordinate, and we have 2 coordinates. It means that wave is transversal. Yeah, electric field oscillates in the xy plane. And these 2 oscillators, they have a common frequency, omega, the same wave vector, and they have a different amplitude and different phases. Depending on the value of amplitude and phases, the trajectory of the tip of electric field vector in the xy plane can go either along the straight line, then we are talking about linear polarization of light, or it can depict a circle, and then we are talking about circular polarization, and more general polarization for arbitrary amplitude and phases. It's elliptical trajectory in xy plane, and we call this ellipse ellipse of polarization. And it can be parameterized by 2 angles. Angle theta is the azimuth of the main axis of polarization ellipse, and epsilon is ellipticity angle, which varies from 0 for the linearly polarized light to 45 for the circular polarized light. This is the description which is well suited for the polarized light. And it means that if we exclude the special dependence on z, so we fixed the point on the z axis, we can describe the wave by the complex vector, which is called Jones vector, and it combines 2 complex numbers. We recognize this amplitude and phase of the x component and amplitude and phase of the y component. And this Jones vector describes totally polarized light, and when this light interacts with the sample, and sample modifies somehow the state of polarization, so we can introduce the Jones matrix, which describes the transformation of this input Jones vector of the incident into the output vector of the light which was reflected or transmitted by sample. And in this table, you see just a few examples like horizontally polarized light, vertically polarized plus minus 40, right-left circular polarized, it's French abbreviation, circulaire droite, circulaire gauche, and elliptical, most general. Yeah? And we cannot measure ellipse of polarization because the oscillation frequency is very high. What we measure is intensity, and we know that the intensity is the square of field amplitude. So if we use our description of the electric field, so we can write in the Jones vector, we can write this equation. If we think about two beams with the polarization state described by the Jones vector J1 and J2, the intensity of these two superimposed beams, of course, it will be the square of the intensity of the total summed light beam, and we can sum the complex amplitude. But applying this formula, we see that actually the intensity, total intensity of these two superimposed polarized light beams, it's a sum of intensity of each beam plus something extra. And this extra is the term which describes the interference of these two polarized states. And we call the two states are orthogonal when there is no interference for any relative phase of these two beams. It means that the sum of the Jones vector of these two polarized states is equal to 0. And it means that in the xy plane, we can represent them by two counterpoint orthogonal ellipses. And I'm sorry, in my screen, it was perfectly orthogonal. Now, because of distortion, the main axes are not completely orthogonal, but they should be orthogonal. And the optical elements, which are characterized by the orthogonal polarization eigenstates, they are called homogeneous optical elements. And you see the examples. Retarders, it's the element which have a different optical paths for the orthogonal polarization eigenstates. It means that they possess the anisotropy of refractive index, yeah, because our optical path is the product of physical path by the refractive index of the media. So it means that when polarized light passes through this element, optical element retarder, it accumulates the phase shift between the two eigenstates. And the Jones matrix for this type of optical element, it's a unitary matrix. It can be diagonalized. And this parameter is called the scalar retardance, phase shift, which we introduced between the two eigenstates. Another example of the homogeneous optical elements, it's a diattenuator. It's an element which possesses the different transmission for two orthogonal polarization states. And the simplest example of such elements is a polarizer. And this element has a different transmission. So they do not change the relative phase, but they do change the amplitude of the components of electric field. The Jones matrix of such elements is Hermitian, and it can be diagonalized. And from the values of diagonal elements, we can calculate the scalar diattenuation D, which characterize the diattenuation property of this element. And up to now, we talk about completely polarized light. But what if the tip of electric field vector describes the random trajectory in an xy plane? It means we cannot describe it deterministically. So it's kind of disordered motion of electric field. So it means that we can describe it only in terms of the probability distribution. And actually give us the incoherent superposition of totally polarized light. But in the linear optics, we measure the intensity, and the intensity is the second moment of the probability distribution. And if we will create the linear combination of this second moment of the components of the Jones vector and average them spatially, temporally, and spectrally, we will obtain the measurable quantities, intensities, and we construct the vector from these 4 quantities, and we call it a Stokes vector. And the beauty of this description, as we now dealing with the intensity, not with the complex amplitude of electric field, Stokes-Mueller formalism can describe fully polarized, partially polarized, or completely depolarized light. So it's more general description. And it can be shown that this partially polarized light, if we will trace the trajectory of electric field, it will make kind of partially polarized. It means that we still can have kind of envelope limiting the motion of electric field vector, but it's not a perfect ellipse. And it can be decomposed, can be represented as a sum of totally polarized light, which has this polarization ellipse, and totally unpolarized. So we have a ellipse which is fully filled with the possible location of the tip of electric field vector. And in terms of the Stokes vector, it can be represented as a sum of Stokes vector fully polarized light and fully unpolarized light, where parameter p, which is a square root of sum of squares of 3 last components of the Stokes vector normalized by its first component, is called the degree of polarization. You see that for the totally unpolarized, degree of polarization is equal to 0. And for totally polarized light, this parameter is equal to 1. And if we want to describe the interaction of the totally polarized, partially polarized, or completely depolarized light with the linear optical system, again, we can write a simple matrix equation that the Stokes vector of the incident light is transformed by the sample into the output Stokes vector. And we are dealing with linear optical system, so it will be the system of linear equations, and it means that this matrix is 4 by 4 real valued matrix, which we call Mueller matrix. And obviously, the optical property of the sample, they are encoded in the coefficient of this Mueller matrix. And if we want to know them, we need to measure this Mueller matrix coefficient. And this is the schematic illustration of the general principle of any polarimetric technique. Like we have a light source which produces unpolarized light in general. It goes through the element which we call polarization state generator. And so we produce a polarized light. The beam interacts with our sample. It's in transmission, but it can be in reflection. Polarization ellipse is modified, yeah, so it can be even scrambled, depolarized. And then the light passes through the element which we call polarization state analyzer. And finally, it's detected. The intensity of the light is detected. So this is the general principle of any polarimetric technique. And just to show you a few examples, the simplest one, polarized light imaging. We place our sample between 2 cross polarizers. It means that the eigen axe, transmission axe of the first polarizer, and the which we call the generator, and the analyzer, they are set orthogonal. And these are the examples of these polarized light images. They usually are very colorful. And this is the section of deceased ivory, and this is the liquid crystal image in transmission. And this technique can be considered as a background free. It means that no signal for polarization in active sample. For example, on this first image, the dark spots and dark lines, they correspond to the eigenax position. It means that polarization was not modified by the sample. It was the eigenpolarization for the sample, and it was completely blocked by analyzer. But this technique provides nice images, but difficult to quantify. So a bit more sophisticated variant of this technique, it's orthogonal state contrast image. We take two images, one when the analyzer is aligned with our polarization state generator, and another when it's placed orthogonal to the eigenax of the generator. So we detect two intensity and we make a differential signal, E parallel minus I perpendicular. And we normalize it by the total intensity. And you see the two examples. This is the conventional standard image. It's a composed scene from the different objects like foam, wood, metal, sandblast aluminium. And right, it's orthogonal state contrast polarization image. And it's easy to see that plane which is made from metal looks completely different compared to the plane made from plastic. But if we want to measure, to have the most complete information about our sample, so it means if we want to measure the complete Mueller matrix, what do we need? This is the general scheme of complete Mueller polarimeter. Again, we have this element polarization state generator. And obviously, to measure 16 coefficient, we need to do at least 16 measurements. And these 16 measurements, they are done in a way like we produce the modulation matrix, which is composed from 4 basic Stokes vectors. It means that we generate 4 different states of polarization and shine each state on a sample. It's modified by the sample and goes through the polarization state analyzer, which in turn is characterized by the analysis matrix A, which is composed of the also 4 basis Stokes vectors. And these Stokes vectors form matrix A. Yeah? And it means that what we measure at the end, detector is placed after the PSA. We measure the raw intensity matrix, which is a product of this modulation matrix, Mueller matrix, and analysis matrix. And if we know all, we know matrix B, we know matrix A and W, we can calculate our matrix A by simply calculating the inverse of matrices A and W. And it gives us the first indication about the optimal design of our polarimeter. These two matrices, A and W, they have to be as close as possible to unitary, not to amplify the error propagation. It means that we need to optimize their condition numbers and what are the parameters which we have at our hands for their optimization. Of course, it's the choice of this polarization state. It means that we have to choose these polarization states which are characterized by the Stokes vector S1, S2, S3, S4, and the same on the output arm to get a good matrices which are close to unitary one. And doing this, we measure and calculate our Mueller matrix of the sample. And the system is calibrated, at least the instrument which we built in our laboratory, by the original eigenvalue calibration method, which was developed more than 20 years ago in 1999 by PhD student in our laboratory, Eric Campa. And this method is the typical feature. It doesn't require specific samples for the calibration. It's just standard polarizer and wave plates. And it doesn't require the precise optical modeling of all optical components of the instrument. And that is the photo and optical layout of the imaging, wide field imaging Mueller polarimeter, which was used in our studies, and the results I will show you later on. It operates in the visible spectral range because we use the ferroelectric liquid crystals as a wave plate, and the acquisition time for 16 raw intensity images for non-optimized instrument is about 8 seconds, and the accuracy on the normalized matrices, normalized divided by the total intensity, it's about not more than 2%. And the field of view, it's a wide field, it's not a microscope. A field of view can vary from 2 to 7 centimeters. And this instrument was built in the laboratory and installed and tested at the pathology department of the French hospital Institut Mutualiste Montsouris in Paris. And up to now, I was talking about the instrument which can provide us this data. But then when we have this 16 coefficient of Mueller matrix, we know that all sample properties are hidden there. But how do we extract them? We need post-process this Mueller matrix data. And classical physical approach, if you have the experimental data, you need to build electromagnetic model which will relate the physical property of the sample which we measure to the experimental Mueller matrix. But what to do if this model is not available, or if it's too complex, which is the case for biological tissue, if we want to measure biological tissue? Then we use the approach which we call phenomenological. It means that starting from the experimental Mueller matrices, which we measure, we decompose, we post-process them. Yeah, we decompose them in a set of simple Mueller matrices, which have a straightforward physical interpretation, like Mueller matrices of a retarder, the attenuator, or depolarizer. And it gives us the clue how to interpret the polarimetric properties of our sample. And this field of optical polarization, Mueller algebra, is very well developed, and there are a lot of books published on this. But we focus and we use in our studies two particular nonlinear compression algorithm of Mueller matrices. It's one which is called product decomposition, named after two persons, Lu and Chipman. And it was shown that any depolarizing Mueller matrix can be represented as a product of the three Mueller matrices of basic optical elements, the attenuator, retarder, and depolarizer. And we know that matrix product doesn't commute, so order matters. So it's exactly this order. And the second, it's the parallel decomposition, or Claude sum decomposition. It was shown by Jean-Claude that any depolarizing matrix can be represented as a weighted sum of four non-depolarizing Mueller matrices. And these weights, lambda 1, lambda 4, it's the eigenvalues of the covariance matrix of our Mueller matrix. So we have algorithm to interpret our data. And now I want to show you how it works. First, it's Lu-Chipman product decomposition. We measured the composed sample. You see in the field of view the piece of the quartz plate, which is a birefringent material, the container filled with the diluted milk, and a tilted glass. So we expect that these three elements will demonstrate they possess these basic properties which we are looking for: the attenuation, retardance, and depolarization. On the right panel, you see the images of Mueller matrix, which we measure from this sample. And it's very colorful, a lot of information, but a bit difficult to understand, like what is hidden inside. So we applied pixel-wise the product decomposition, and that's what we obtained. This is the map of depolarization. And indeed, we see that this right top corner, milk, it's a scattering medium, so we expect it to be depolarizing, and it possesses the highest depolarization in this scene. Retardance correspond to the quartz plate, which is also expectable, and dichroism, the incident light, is polarized in backscattering. It's the tilted glass. So it's the result which we expected. So we checked that it works well. Next, we start measure the biological samples. Here you see the photo of the excised fresh colon specimen. It was a colon tube which was excised because of this, you see red spot, the cancerous polyp. And we took the Mueller matrix images, 5 by 5 centimeter. Again, the image is a bit distorted. I don't know why, but it was a square 5 by 5. And right panel, you see the Mueller matrix of this cancerous polyp. The measurements were done at 550 nanometers. And Mueller matrix looks quite simple. Yeah, it's a diagonal one. And we did the measurement of many colon specimen, and to represent the typical trends with the wavelengths, these are the typical value of the diagonal Mueller matrix coefficient. M22 was equal to M33, so we plot only M22 and M44. And M22 represents the degree of depolarization of linearly polarized light. M44 states the same for the circularly polarized light. And from this plot, it's clear that the Mueller matrices are diagonal, so it means that the tissue acts as a partial depolarizer. We didn't observe on this type of tissue no retardation, no significant attenuation. Then we observe that the values of M22 elements shown by squares, they are always higher than the values of M44, and this relation holds for both cancerous parts of colon tissue and healthy. Cancerous shown by red and healthy by black symbols. And this behavior is typical for the small scatterers. So we are in a relay regime. It means that what is backscattered on the particles which have a special scale smaller than the wavelength of our light. Yeah? And taking into account that wavelength is less than 1 micron, it means that what we measure is not backscattered by the cell's nuclear, because the typical size of cell nuclear is few microns. Then we observe that the sign of M44 is always more than 0 in our experiments, and it means that it was like mirror type scattering, which changed the helicity of the backscattered photons, and this is a dominant mechanism. And this drop in value of Mueller matrix coefficient, which corresponds to the increase in depolarization of detected light, we attributed to the decrease in absorption of hemoglobin, which is the main absorbing component of tissue in this wavelength range. It has peaks at 500 and 550, and in the red part of the spectrum we have a significant drop in absorbance. It means that photon can travel longer, exhibit more scattering, and be more depolarized at the detector. And so we show that this technique works. It shows some interesting results. And the next application we explored, it was the screening for cervical cancer. And why is it important? The cervical cancer is the fourth most frequent cancer which affects women around the world. And if you see the color, it's the primary cause of cancer-related deaths in the developing countries among women. So this is the schematic cross-section of the uterine cervix. And it's already established that majority cases of this disease is due to the infection by the various types of human papillomavirus, HPV. And usually the infection starts from this part, which is called ectocervix. Yeah, it's the part of the uterine cervix which is exposed to vagina. The infection starts from here, and you see the schematic, schematic histological cross sections of the epithelium of this part of the uterine cervix. This is the normal squamous epithelium, and when the virus starts produce the malignant cells, there is an invasion of the epithelium. So it starts from the basal membrane and invades the whole thickness of epithelium if nothing was done. Yeah? So when the whole epithelium is invaded by the malignant cells, we are talking about the severe dysplasia or cancer in situ. And if nothing, if it was not treated, so it breaks the membrane and it becomes an invasive cancer. The total thickness of this layer is less than 0.5 millimeter, and the process is very slow, so it takes up to 10 years to develop, so which makes this cervical intraepithelial neoplasia conditions a very suitable for screening, like for checking, because when it's detected on early stage of low cervical intraepithelial lesion, the simple surgical intervention, like just cut piece of the cervix, and it's a cure for this disease. So the program for eliminating cervical cancer, according to World Health Organization, includes 3 steps: prevention, screening, and treatment. And I told you why is it interesting to make screening, because it can save the lives. And in the developed countries, starting from certain age, each woman goes through the pap smear test check, cytology analysis. It means that the cells from the part of this ectocervix part are collected and examined under the microscopy after staining. If the bad cells are found, the next step is colposcopy. It's examination with the special instrument which is called colposcope, and it's just a magnified view. So what is seen by this instrument, it's the uterine cervix. But the problem with the cervical intraepithelial neoplasia that it has very low contrast. So the lesion could be already here, but you do see nothing. And what we suggest Mueller imaging polarimetry. And to check, we did a proof of principle studies. We start with the ex-vivo images of the fresh cervical specimen. It means that the woman was already diagnosed with this pathology and underwent the surgical procedure. So the piece of the uterine cervix was cut. And you see, this is the total intensity image. It went through the standard pathology analysis. You see this map created by the pathologist. The vertical lines, they show the location of the cuts where these thin slides were prepared, stained, and analyzed by the white light microscopy. And the reconstructed map of the lesions looks like in the center we have the zone of severe neoplasia. Left part is a healthy tissue of uterine cervix and some benign conditions in the right part. Sorry. And right panel shows you Mueller matrix of this sample. And contrary to the colon tissue, now we see that it's a full matrix. Yeah, it's not a diagonal matrix. So it means that this matrix, this tissue is not only depolarizing. There are other polarimetric properties which are hidden, coded in these encoded Mueller matrix images. And as we did for ad hoc sample, we applied pixel-wise this Lu-Chipman polar decomposition. And I put here again this pathology map and the maps of the scalar retardance and depolarization, because we didn't see significant diattenuation. And what is interesting, in the central zone of cervical intraepithelial neoplasia, it's highly contrasted with respect to the healthy tissue. So healthy tissue demonstrates the retardance up to 60 degrees, and it drops to 0 in the zone of cervical intraepithelial neoplasia. In depolarization, we also see contrast, which are not visible in the total intensity images. And again, this zone of pathological zone is less depolarizing compared to healthy tissue. We examined the healthy cervical specimen. It was the total hysterectomy because of other pathological conditions, and the medical doctors prepares for us this conization. The piece was healthy. You see white line. They show the position of the histological cuts. This sample was also analyzed by a pathologist and confirmed that it's a healthy tissue. And we see that the depolarization is very uniform, and scalar retardance also has very high value up to 50 degrees. And to summarize the trends for the fresh uterine cervix specimens, that's what we observed for scalar retardance and depolarization depending on the tissue conditions. Retardance drops already at the low, mild degree of neoplasia, and the depolarization decreases gradually. So it gives us hope that combining these two parameters, we can perform optical diagnostics. And after that, we did preclinical studies with the 3 French hospitals. And this is, I show you the intensity images of cervical specimen of 24 patients. Again, the patients, they were diagnosed by doctor with this pathology, and they underwent this surgery. And on top, you see this colored, rendered in green and red pixels. So this was the pathology diagnosis reconstructed from the histology analysis and superimposed on this total intensity images. So some pixels are unlabeled, so we don't know the conditions. But those which show green color, we are sure that this is a healthy part of tissue, and red, this is the cancerous zone. This is the example of the Mueller matrix measured for the fixed cervical specimen. The color bar is different here, but you see that the matrix is not diagonal. It's also complete Mueller matrix. And we did the same. We applied the Lu-Chipman decomposition pixel-wise, and that's what we obtain. I show you the image of scalar retardance for one sample. I do not show the image of depolarization because it was all flat, no contrast. And you see on this image the vertical line which has a colored segments, and these colored segments, it's actually the histological diagnostic as provided to us by the pathologist. And for a moment we are interested in binary diagnostics, like we want to detect this red, which is really the condition which requires the surgical intervention. And what we did, we take the images of scalar retardance and depolarization, and we calculate pixel-wise the sensitivity and specificity of our diagnostic, putting a certain threshold on the values of scalar retardance and depolarization, and using the histology as a gold standard diagnostics. It means that we check if pathologist says that this is a deceased pixel, and from the value of scalar retardance, we also say, yeah, it's deceased. It means that we are okay. We correctly detected the deceased pixel, and the same for the healthy pixels. And based on this sensitivity and specificity, we plot the AOC, we plot the receiving operator curves and calculated our performance metrics area under this curve. And this curve, it's nothing else as the sensitivity is a function of 1 minus specificity. And for ideal observer, which correctly identified all healthy and deceased pixels, the value of AOC should be 1. And for completely random, it should be 0.5. It's like straight line here. And for two metrics, for two optical markers, which we use as decision variables for the detection of this CIN of high degree, retardance and depolarization, we got the value of AOC 0.94 and 0.5. So you see the depolarization calculated from Lu-Chipman decomposition works not better than the random guess. So we may just randomly assign healthy or diseased pixel, and we'll get the same performance. It means that depolarization doesn't do the job. Why is it so? Is it intrinsic property or something else? And to address this question, what we did, we plot the histograms of all labeled pixels. You see the probability of occurrence as versus different value of scalar retardance and different value of depolarization index. We plot as a 1 minus depolarization index. And from these histograms, it's clear that we see two families. The blue, it's the pixels which are labeled as a deceased by anatomopathologist. And you see that they are shifted to the low scalar retardance values. And the healthy pixels, it's a distribution which is less peaked, but shift to the higher retardance value. That's why it shows a good detection performance. And the same histograms for this depolarization index, they almost completely overlapped. That's why we cannot use it as a decision variable. It has a very poor detection performance. But we know that tissue is very depolarizing, so there should be information about tissue conditions hidden in these depolarization properties. So to check this, we applied a different decomposition, different nonlinear compression of Mueller matrix data, which I mentioned before, closed some decomposition. And we use a vector matrix of depolarization because three smallest value of the include decomposition, they characterize the depolarization property of the samples. And using this smallest eigenvalue as a decision variables, we calculate the AUC, the detection performance of our matrix was 0.93 compared to the value of scalar retardance AUC. And these are the images of 3 patients which has both healthy and diseased zones. And at the bottom you see the scatter plots. It's the differential value of these eigenvalues. And for all 3 images, we do see the clusters in these scatter plots. So it means that they are separable. That's why changing the metrics for depolarization, we can use it as a marker for tissue diagnostics. And this table sums up, because we tried a different metrics, the scalar retardance from Lu-Chipman decomposition, depolarization index, entropy of coherency eigenspectrum, 4 eigenvalues, smallest eigenvalues of coherency matrix, and eigenvalues plus scalar retardance. And we see that like the family of 4 markers show almost the same high performance, good diagnostic performance. So one should take care about choosing the data post-processing algorithm when doing Mueller matrix polarimetry for biomedical diagnostics. And the next application I want to talk about, it's the visualization of exact border between tumor and healthy brain tissue during neurosurgery. The white matter of brain is made of fiber tracts. And these fiber tracts, they connect the different area of a brain. It's like cables. And these tracts, they are responsible for the specific function like vision, speech, motion. And when brain tumor starts to grow, its cells grow chaotically, and the most dangerous one, the glioma and glioblastoma, they start to grow inside the white matter of brain, and they break this ordered structure of healthy brain. But to see these fiber tracts during surgery, it would be a big breakthrough for neurosurgeon, because it will help differentiate the healthy brain, which has a structure, from tumor no structure. And I will show you on the next slide. Yeah, the problem is that this is the surgical room of the hospital, and this is the field of view seen through the surgical microscope. The fiber tracts of white matter of brain, they are not visible on the intensity images. So there is no contrast between tumor and the surrounding tissue. There is a structural difference, but there is no visual difference. And this is the cross-section of a brain in the coronal plane, just to explain what kind of studies did we perform. The proof of principle study. The outer shell, it's like 1-2 millimeters of gray matter. It consists of the neuron cells and axons, which connect them to another neurons. And these bundles of axons, which run through the white matter of brain, they form fiber tracts, and they have a high anisotropy of form. And when tumor starts to grow, this artistical representation renders tumor in pink, so it's visible, but in reality it's not visible. It pushes the brain fiber tracts, so it's very close, yeah, but it doesn't have any contrast. And the technique which can help neurosurgeon to see this structural difference between tumor and healthy brain would be of great help. So the proof of principle studies which we did, this is the schematic of the specimen which we studied. This red dotted line, they show the position of coronal plane, like the human brain tissue from anonymous donor autopsy was cutted, thick piece was cutted in coronal plane, and you see two adjacent pieces. One went for polarimetric imaging and another went for the histology images. On the right panel, you see the whole mount thin section, which was stained with the silver, which is a gold standard for the ex-vivo visualization of brain fiber tracts. This this specimen went for the studies with our instrument. And these are already Lu-Chipman decomposed maps of the measured brain tissue. We immersed it in the water, so the white spot which you see, just specular reflection of our light from the water-brain interface. And we do see the image of depolarizations, color retardance, and azimuth of optical axis. On the depolarization image, we see that this dendroic structure, like highly depolarizing white matter, because it's more dense compared to the white matter. Scalar retardance also showed us this nice structure with the border between the gray and white matter. And when medical doctor who brought us the sample saw the azimuth of optical axis, he told us, I've never seen such image, because he identified the thick fiber track which runs vertically, and you see this circular color code scale. Red it's vertical, blue is horizontal, and green and yellow it's plus minus 45. To have a closer look, what we did, we took the image of the map of azimuth and we enlarged the zone of so-called U fibers. It's the U fiber, it's fiber which connects the neighboring part of cortex. And when the size of this image, it's 70 by 60 pixels, and we do see very nice orientation which follows the direction of U fiber. And this zone with the random orientation, it's a cortex where there is no structural elements. And at the bottom, you see this silver stained thin mount, which was examined with the microscope, and also we zoomed more or less the same zone. And we picked up the zones in the map of azimuth and in this enlarged microscopy zone. And we calculated the circular histograms for the azimuth of optical axis, and we enlarged the microscopy zones. And you see a very compelling correlation, like vertical orientation of the direction of azimuth of optical axis, which has to be aligned with the direction of axons. And these axons, which are vertical at the bottom panel, and this holds for the vertical minus 45, horizontal plus 45, and completely random orientation for the zone of the cortex, because it's partial resolution of our instrument. 1 pixel is about 200 by 200 micron. We do not see any structural anisotropy. The next sample we studied just to check if formalin fixation induced some artifacts. We just bought it's called in the paper fresh cadaveric cuffed brain, but actually it's just food. In France, in a butchery, it's called the cerveau de veau, and we cut the same like thick section in coronal plane 1 centimeter thick section. This is without formalin fixation. We just rinsed it with the water to remove the blood clots. And these are the images of this calf brain specimen: intensity image, depolarization, scalar retardance, and azimuth. And again, we do see this dendritic structure with a highly depolarizing white matter, scalar retardance, and this azimuth, where we can see the thick fibers running vertically and horizontally, and again, these U fiber type structures. So the results are quite promising. And to conclude my talk, the multispectral wide field Mueller imaging polarimetry is sensitive to tissue microstructure. It can probe tissue at different depths by doing spectral scan. It's a wide field imaging modality, a few square centimeters, so it doesn't require the special scan to take image. And it's not an expensive one. It can be implemented at relatively low cost, and we can also add that it uses visible light, so it's not harmful for the patient. And we believe that the enhancement of contrast, which we demonstrate, highlights the difference between the healthy and cancerous zone of the polarimetric images of biological tissue. And we attribute the better preservation of backscattered light from cancerous zone by damping of scattering and increase of absorption in the cancerous zone. And we are sure that the relevant optical markers of cancer can be the depolarization and both scalar retardance and orientation of optical axis. And I would like to thank you for your attention and to acknowledge the funding and the work of PhD students and postdocs in laboratory, our collaborator and staff members.
Okay, great. Thank you, Dr. Novikova. So we have several questions, and I will, so we have a little bit more time, I guess. So let me ask the first one. I just want to make sure I understand it correctly. Is Mueller matrix only use, let me rephrase this question. It looks like Mueller matrix is highly intensity sensitive. Is it the case, I guess?
The Mueller matrix, let's say, M11 element represents the intensity. Usually all images which I showed you, they are normalized by intensity. So the properties which we extract from the measured matrix, they are not prone to the variation of intensities. I don't know if this was the question.
I believe so. So second question, what morphological features in biological tissue, thin and benign, cause retardation of polarized light compared to healthy tissue?
Probably this question goes to the cervical specimens studies. Yeah, we believe that it's extracellular collagen matrix which provides this value of retardation, because as I told you, in backscattering configuration, we do not collect light from the cells in epithelium, because at least light scattered on the nuclear of cells. They are large. The scattering on the cell's nuclei is very anisotropic. All signal goes into the tissue, but we don't have detector inside the tissue. And what we collect in the back scattered configuration, it's scattering on the small, on the cell suborganelles and on the collagen fibers. And we did the microscopy studies. I just didn't have time to show this in 1 hour for the cervical tissue, and we are pretty much sure that it's underlying let's say quite dense, about 300-400 micrometer layer of collagen, which causes this birefringence of healthy cervical tissue. And this collagen matrix is destroyed like when neoplasia is confined to the epithelium, so everything at early stage, but it already starts to remodel the underlying collagen extracellular matrix, because it needs to arrange it to have a vascularization, the food supply. And this is the reason for this birefringence, for the loss of this birefringence.
Okay. A question from Dr. Jung. If I am understanding correctly, does the procedure need initial data from some other approach, for example, histology, to understand what we would expect as the Mueller matrix values relate to cancerous versus non-cancerous regions?
It's again like we have data, and here we validate it against histology, because if I will say to doctor blindly low retardance, it means you have cancer here, and he will say me, what does it mean low retardance? So we use here, it was a, let's say, preclinical proof of principle study to show, to have a ground truth that indeed there is a correlation between histology and low retardance value. But once you establish this relation, that the state of your collagen matrix, which is destroyed by cancer, and it's really an indicator of something wrong going in your tissue, then you can use it without checking every time versus histology. You have to prove first that your method works. So histology, it's kind of a gold standard validation method. But if we assume
so it's at the validation stage. Mm-hmm.
Yeah.
But it's not a minimization approach, so it does not require pre to know a priori. It's just at this stage you're using histology to validate.
Exactly.
All right. So great. So in slide 32, using histological standard, how are the polarization image classified process to be comparable to the different condition, if at all? Is it a combination of the polarization over or Mueller matrix parameter, or can some components correspond more towards each histological method? Thank you very much. Slide 32, I guess.
This one, yeah?
We don't see it. You're not sharing the screen.
Ah, okay. But I didn't stop. You just dropped me. Just a moment. This one. Do you see my screen?
Mm-hmm. Yes.
So the question was about
how are the polarization image classified to compare to different conditions?
This is just what is shown is a color retardance from 0 to 40 degree, and the colors we use this jet color scale. So you see blue region, it means that the in this region it's below 10 degree, and I mean, of course, when you calculate your sensitivity and specificity, there is one parameter which you need to define. It's your threshold value. Because if I put my threshold value to 0, and I will say everything is deceased here, it means that I will have a super sensitivity, yeah, because I will correctly identify all deceased pixels. But I will have a very bad specificity, because a lot of healthy pixels will be tagged as a deceased pixel. And the same if I will say everything is healthy. So it means I am okay in terms of specificity, but I am very bad in terms of sensitivity. So it's always kind of trade-off between these two parameters. And in case of the scalar retardance, you see it varies between 0 and 50, I think, yeah. If I put the value of scalar retardance threshold 10 and say that everything which is below 10 it's deceased, and what is above it's healthy. That was my method of selecting from optical diagnostics the set of healthy and deceased pixels. I don't know if I answer your question.
Yeah, I think that was clear. There is a question about the thickness of the sample in slide 16, and if the PSG was assumed constant across cervical depth. So slide 16.
This one.
I suppose. Yeah, so
but
so I mean your images are done all in transmission. So yes, the PSG is assumed a constant across the thickness of the entire slab, right?
Okay, this is a schematic. I mean, it's shown in transmission, but it can be in reflection as well. It's not a thickness of sample, it's just box which shows the sample. So
right. Yeah, no, I think it has to deal with, it's not a confocal approach, it's not polarization sensitivity. This is a transmission or a total reflectance approach. So the PSG stays constant.
I mean,
it's not changed depending on thickness of the sample.
No. It's like it doesn't interfere with the thickness of the sample. It's the same modulation matrix. We choose it once when we do this design optimization.
Right. So I have another like 10, 15 questions here, but I think we're running out of time because we were supposed to. You have a meeting with the next professor. So I thank you once again for this very informative talk, and then the students have a meeting with supposed to ask question beyond and.
Okay.
Maybe that I see Tashawn has questions and many others. So that's and to ask this question again. In the meanwhile, we thank you.